like it means nothing.
Thank you very much, everyone. We're almost done for the weekend. I think this is one of the last talks, so well done if you're still here. What I'm going to be talking about today is not the title there, it's this title. We're going to be talking about protocol attacks, and protocol attacks that derive from taking messages out of order. So my name's James. I'm based in Manchester in the UK, and as you're probably going to learn through the content of this talk, my kind of area of interest is network protocols, a bit of reverse engineering, and anything that's a bit weird. So when we have a job like, oh, there's this weird network thing, let's have a look at it. And that's what we're going to be talking about today. So we're going to talk about two things today. We're going to talk about a protocol you may or may not have heard of before, something called IPMI. Then we're going to be talking about how to exploit protocols in general. And we're going to show some practical techniques for doing so, a bit of reverse engineering, a bit of fuzzing. And finally, we're going to show how you put these two together and you do practical reverse engineering and exploitation of an IPMI protocol. So, part one, how to turn on a computer. To do this, we're going to tell a bit of a story. So this is Adam, and Adam's best friend is a Windows ME domain controller. Unfortunately, his friend has a bit of an issue sometimes, which is that he likes to crash. And when a server crashes, it can't be turned back on. And what he has to do is physically go up to the server, click a button, and back online it comes. So that's not too hard, right? But now, his domain controller's in a server room, somewhere else in the building. So it crashes, and all he has to do is go across the building, unlock the server room, go in there, press the power button, and it's not that hard, but it takes about, let's say, 10, 15 minutes. Now the server is in a data center. So he could drive down over there when it breaks, but instead what he does is he phones up his mate, the IT admin that works in the data center, and it still gets resolved, but it takes a little bit of time. And now we have the domain controller, or the server, back in the data center. But this domain controller can't be reached. It's on the other side of the world, and there's no one there to administer it. So there's no one you can phone to turn it back on. So what happens when this crashes? How do you turn it back on? Well, what we're going to talk about is a protocol that allows you to click a button on your laptop over the internet and turn on a computer that's actually offline. So its operating system isn't running. You might have heard of this, and if you have, you've probably heard of it as one of these things that we're about to show here. So HP ILO integrated lights out, Dell's integrated remote access controller, or iDRAC. Cisco have a thing, Supermicro have a thing. They've all got different proprietary names for it, right? These are examples of what we call baseboard management controllers. And what they allow you to do is turn a server back online, or, as we'll see, talk to its hardware when the server itself is not on, so independently of the main operating system. And the way this works is you actually have a separate computer, a separate physical computer attached to the motherboard. Sometimes that's a second chip built into the motherboard, sometimes an expansion that's built into something like a PCIe slot, and actually what we're going to be talking about later today are virtual BMCs, so actually pieces of software that run on top of an operating system, and they allow you to talk to virtual machines, but it does the same thing. So the idea of these devices is that they have hardware-level access to the, let's call it the host, right? So the main operating system, like the Windows and the motherboard. And they allow you to do things such as what we call chassis control, so turn the system on and off. That's what Adam was doing. He was pressing a button to say, please reboot the machine. And it also allows you to alter other hardware. So you can look at fan speeds, temperatures, you can read sensors, and you can send commands. So you could say, make the fans turn up because it's overheating a little bit. We'll also go on to see some other examples. It's vendor-specific, but some BMCs allow you to do things such as like the capabilities of a BIOS. So you can interfere with secure boot, boot devices, various inputs and outputs. Again, it's dependent on vendor support for those, so it really varies per type of device. But there's capabilities beyond just hardware stuff. You can actually look at the kind of the OS that's running and where it's being loaded from. And the key part of this is that it's accessible over a network. And we're going to be talking about network protocols, and that's why this interests us. So we're going to look at the security of some of the software that allows you to do this, and why it might not be the best idea ever to be exposing this. So the protocol is called IPMI. You don't need to know what it stands for, but there's a document. We'll have a link to that later if you want to look it up. But it's a network protocol that allows you to speak to a BMC. And what it allows you to do is two things in general. Send commands, so a command such as turn the system back on, turn it off, and also retrieve sensor data. So again, tell me the fan speed, tell me the temperature, tell me what devices are connected. And this is exactly the protocol that allows Adam to remotely turn a computer back on over a network by speaking IPMI. If we look at the history here, that might be too small to make out, but you don't need to read it in depth. It's actually originated in 1998, so it's a pretty old protocol by now. We don't actually care about the original version. We care about version 2. That's still incredibly old now, 21 years and still going. So version 2 from 2004 introduced some new security features, which aren't that great, but that's the newer modern version of the protocol. And the way these work in terms of security properties, we'll go on to talk about what some of these do a bit later, but it offers encryption effectively. So we have message signing and integrity to stop people tampering with them. We have symmetric encryption to stop people sniffing the messages. And we have different cipher suites just shown in a table on the right, if you're interested, that allow you to do that. So a bit like TLS, you can swap out cipher suites as meets your support. So for example, hardware support might support different types of strengths of cipher. Also crucially, as we'll go on to see when we discuss exploitation, it has this concept of users. So IPMI can support different users, and each of these users can have a different level of privilege. So there's a little table there, but effectively you can be a low privilege user, and a low privilege user might be able to do something like read the temperature or read the fan speed, so consume sensor data. But you can also have admin, and an admin will be allowed to do things like turn off and on the machine. So obviously when we're looking at security, this is of interest to us. And the encryption ties back to the users via a password. So the keys used to authenticate a user and secure your connection are derived from your password, and that is how a user proves who they are to access the system. So we're going to look at the protocol in a little more detail. So here we have a client server. We'll show the message communications on the right and a bit about what they do on the left. So if you have a client that wants to talk to a server over IPMI, the first thing you do is get authentication capabilities. This is very common in a lot of protocols. It's effectively saying, let's negotiate cipher suites. So we both agree on a set of ciphers that we can talk, that we both support, and we can actually communicate with one another. You then do an open session request. So you actually say to the server, hi, I'm a client. I would like to authenticate. And then you begin the actual authentication process. This is split into two parts. And the first part via what we call the RACP1 and the RACP2 messages. And in this, the client says to the server, this is my username, so I'm Adam. This is the privilege level I would like to connect with that is associated with my user. So you have to actually have that privilege. But for example, I'm connecting with my admin privileges. And we also exchange some random numbers. The random numbers are crucial for this encryption routine. Think of stuff like Diffie-Hellman. So you need to exchange random numbers to authenticate each other and then secure the connection. And then the final stage of the authentication is in messages RACP3 and RACP4. And what this is the actual cryptographic exchange. So you take those random numbers, you sign them with the passwords, both sides prove to the other that they know who they are, they know who the other party is, and via this they establish a symmetric key which they use to encrypt all further communications. And at this point, they can communicate. So they communicate via IPMB messages, and IPMB messages just encapsulate those commands we saw earlier. So again, turn off the computer is an IPMB message. Read sensor data is an IPMB message. And an IPMB response would be, I have turned off the computer, or here is your temperature. It also supports a kind of secondary handshake, a bit like TLS session resumption for those of you that know it, but it's not that important to us at the moment. So, because this is obviously quite an interesting protocol, it talks to hardware. It talks to hardware below the level of the operating system. And people have found it in the past and gone, what's this? It's had some security research done into it. The first kind of major crack at it that I'm aware of is in 2013. some of the folks over at Rapid7 found a bunch of issues, mainly in the cryptography of the IPMI protocol. One of the main attacks is what they call the null cipher attack, which is as simple as in that list of supported ciphers were a bunch of ciphers that said no encryption, no authentication. And a bunch of hardware has this enabled by default. So if you don't disable this option, you can just connect and say, actually, we're going to authenticate, but we're going to authenticate with the null encryption algorithm, so I don't have to authenticate. Also in 2013, a paper came out talking about some of the vulnerabilities in the actual firmware. So again, these are chips running on a motherboard, for example. So it has firmware. It's a separate operating system. This isn't the first example of someone finding vulnerabilities in IPMI firmware, but it's quite a nice case study. And it kind of goes over some of the way they did it and some of the research. Now, they actually did it in an HTTP interface, which some of these systems also have, but we're not going to be looking at HTTP so much. Much more recently, there's another example of vulnerabilities found in supermicro BMCs. The reason this is of interest, and by the way, there were loads of vulnerabilities in between, but the reason I'm pulling out this one in particular is because one of the quotes from the paper says, you can gain enough privileges from this BMC, this separate piece of firmware on a motherboard, to actually gain persistent access to the UEFI BIOS of the host operating system. And there is evidence of nation-state threat actors exploiting these and having written custom implants targeted at UEFI bootkits distributed over IPMI. So you can see now that if you can exploit this little chip or this program, you can really gain some privileged access to the host operating system. And that's why this is, again, quite interesting. And then also very recently, something quite similar in Cisco, but a slightly different vector, but showing that you can interfere with the secure boot chain from these BMCs. So again, separate chip, separate firmware, and suddenly you start being able to interfere with the really core security properties of the host operating system. And because this is happening on a separate piece of hardware, if you've got some network inspection, that might catch it. But no EDR or anything on the host operating system is ever going to see these packets. The host-based firewall is not going to be able to stop it. So you can really see why people are looking into this and why it's an interesting vector for exploitation. And that takes us to the end of part one. So we just showed that BMCs are these weird little chips. Again, we're going to talk about some software versions later. They support this protocol called IPMI. It has encryption. It has users. It has passwords. And research has shown that there's a history of mistakes being made in these systems. So, on to part two. We're now going to take a step back from IPMI. We'll come back to it later. But we're going to take a step back from it and look at protocol exploitation in general. So, first off, what do we really mean when we say protocol exploitation? So, we really mean kind of network protocols, right? So anything where two computers are exchanging bytes over what we regard as a network, so maybe Ethernet-based, maybe Wi-Fi-based. Here I've kind of shown an example of the TCP/IP stack and some of the protocols there. But really, when we're going to be looking at protocols here, what we care about are these ones at the top, so application protocols. And the reason for this is that this is where security lives. IP and UDP and TCP are not authenticated. They're not encrypted. You can have things like VPN, which combine encryption at the transport layer. But really, all the security, all the interesting stuff, that happens up at the application layer. So SSH, passwords, encryption, TLS, also encryption, and IPMI. These are application layer protocols. So when we're looking from a security perspective at protocols, this is generally where we look. The protocols are actually supposed to be doing encryption, and maybe we can find flaws in this. So what are we looking for, and what are we talking about when we say protocol security? So there's a few kind of key ways of looking at it. First off, you have confidentiality, the kind of obvious one. Is the data being encrypted? Can someone see sensitive data by looking at the communications, by just passively sniffing the data? Then we have integrity. So integrity talks about the ability to trust the other party. So are you being intercepted? Is the client who they say they are? Have they proved it? And you saw some of that in the IPMI protocol encryption algorithms. Now, you might be expecting to talk about availability, but actually this isn't quite as relevant And the reason is that as an application protocol, as we saw in the previous diagram, you are sitting on top of a bunch of transport protocols. You are not really responsible for your own reliability of transport. If someone drops packets at the TCP layer or pulls a wire out, there's nothing that the HTTP or SSH protocols can really do to combat that. You can maybe build in some reliability, but not much. At the end of the day, someone might just, drag a ship across a cable, no more availability, no more application protocol. There's nothing you can do to protect against it, really. We do, however, care about the availability of the server. So let's say we have an SSH server. If I can send a packet in SSH protocol, which crashes the server, causes a buffer overflow or something, and kills the server and no one can connect to it, I care about that. That's bad. So we do begin to care about availability of the server itself and actually of the clients. So if I can knock over people's clients if they connect to my server, that's also not great. And since we've begun to talk about actually what happens on either end of the connection, not really just in the middle, we can also look at bug classes such as remote code execution, information leakage. If I can send a crafted SSH packet that exploits the server and gets me a foothold, allows me to run my own shellcode on it, for example, then that is a security flaw in that implementation. And it doesn't just have to be RCE. Again, information leakage, so maybe imagine something like SQL injection where I can retrieve data without actually running my own code on the system. But these are the kind of core themes that we look for in protocol security. And within those, we look for specific, let's say, types of vulnerabilities. So we're just going to kind of really group these together quickly. Cryptographic issues. So issues with the actual protocol itself. Insufficient encryption, insufficient authentication strength. There are some examples there of ones, for example, in Windows systems, where really the weak authentication ciphers allow you to do things like replay them. And then we might have, for example, binary vulnerabilities. So again, buffer overflows. If I can send a bunch of bytes to a C application, I override it, the server crashes, or maybe the server gives me remote code execution. But what I want to really focus on in this talk is a third class of vulnerability, one that's not talked about quite so much. And I'll go on to explain what it is. These are referred to as state machine attacks or state machine vulnerabilities. Now, their impact isn't as often things like RCE. Their impact is much more likely to be, for example, authentication bypass, and in general, logic flaws. So we're going to talk about the logic of protocols and how we can break that instead. And we're kind of thoroughly in the realms of undefined behavior. Weird stuff tends to happen when we exploit this, as we'll go on to see. So to give you an example, I've created a really, really simple, just dummy protocol here. So you can see it along the top right. We start off on, no, it's not working, ping. So that's our first message. Then we authenticate with a password, and then we send some data. And I've written some code for it along the right. So you ping, you authenticate with a password, you send data, you're authenticated. That's how the protocol works, or is supposed to. So now let's think, if I were an attacker, obviously this is pseudocode, but if I were an attacker, where would I look for vulnerabilities in this? So typically, the first place people would look is that validate password function. You'd look at things like buffer overflows. What happens if I just submit a bunch of A's? What happens if I put SQL injection? What happens if I time the differences between a correct and incorrect password? But I'm actually going to show you an attack which doesn't focus on what input you send, or rather the format of the input. So my attack works like this, or rather, this dummy state machine attack. First off, we do a ping, a pong, and then we send data. Because nowhere in that code does it check that you have ever authenticated, does it? Right? And that is what we call a state machine attack. And if we take that diagram, we can kind of explain it like this. We find a bypass that allows us to skip a crucial step, in this case, authentication. It doesn't just have to be that, so that's kind of the most common one, and that's the one we're going to talk about today. But it can also result in you skipping a step that defines a variable being 0, and then because the variable's 0 and the server wasn't expecting it, you get some kind of undefined behavior. For example, if that 0 is an encryption key, you've just bypassed encryption. So you might think, that seems quite simple, right? Like, obviously, if you were writing a protocol, you would check that someone's authenticated. So it turns out that's not the case. And the reason it's not the case is kind of highlighted by this diagram. No. This is the state machine of a real TLS implementation, and you can instantly see just how much more complex it is than our dummy example. Look at how many more states there are and how many more pathways between them. This isn't even the worst one. So you can begin to see that it's actually really complex to begin to find these or notice them in the code of a large real-world server implementation. This is a diagram of TLS, and I'll show a reference to the paper this comes from later. But this is where this research largely has come from. It came from about 2015, looking at TLS implementations, and effectively realized that you can just skip certain combinations of the protocol messages and, again, cause undefined behavior. So this resulted in attacks such as the one I mentioned before, so an encryption key just being initialized to 0 because you skip the step at which it's ever initialized. And then later on, you go to encrypt something, and it gets encrypted with a predictable state. But this is what state machine vulnerabilities really are. It's about skipping steps in protocols, and this leading to vulnerabilities, usually, again, in logic and authentication. Which brings us on to part 3, practical protocol analysis. So we've shown what the vulnerabilities we're looking for are. Now we're going to show some examples of how we can look for them. The first one is source code, right? If you're looking at an open source protocol or a closed source protocol for which the vendor is kind enough to give you the source code, you can just look at it. So clone the project, open it in an IDE, and just look at the code. And the kind of stuff you're typically looking for is kind of the key parts that you'd expect to see security. So look at where encryption is applied. Look at where the password is validated, for example. Does that seem good? Does it feel good? Just learn the kind of ins and outs of the protocol in general. You can also kind of look for specific things. So again, different languages might have known insecure functions. C has a bunch of functions which are known to lead to buffer overflows. So you can look for that kind of thing. And to help you do this, you can do more than just look at it with an IDE. You can actually use some tools to automate this. So I've listed 3 of the most common ones there. But frankly, there are hundreds and hundreds of tools which will look through source code, and they'll look for known patterns of bad, vulnerable behavior. Those are some examples which kind of look at scale, but you can find simpler ones. And even a lot of the C compilers, for example, have tools that help you do this. Now, the thing is, if you don't have source code, you're going to need to get your hands dirty with reverse engineering, which some of you might have been doing in the CTFs here. So reverse engineering, we typically take a binary without the source code, and we're aiming to discover its functionality and a kind of get back to the source code. Now, if you've got a language like .NET or Java, you can really easily decompile these and recover the source code unless someone's done some obfuscation. If you've got a C application or a Rust application, you're going to get your hands dirty. So this is just a screenshot of the tool Cutter, Ghidra, IDA, anything like that. You're going to begin to need to look at the binary, understand what it does, and kind of reverse the logic. It's much slower than having source code because you've got to put this extra effort in to get from the binary to the logic, whereas the source code just shows it to you. But we can still do pattern matching. So in the same way that semgrep, etc., looks for patterns in source code, there are several tools out there that can actually look for patterns in, for example, you can have it in Java bytecode, or these ones look for it in kind of compiled C applications. And you can look for specific combinations of instructions that are known to lead to vulnerabilities, or to specific function calls and that sort of stuff. One thing that comes along with RE is obfuscation. So vendors might obfuscate the binary to make it harder to reverse engineer, and this might trip you up and make your life even more miserable. Moving on from things we do to analyze the kind of static binary or code and looking at dynamic techniques, so techniques where the code is running, debugging. Now, debugging is about looking at a running application, understanding what's going on under the hood. So typical tools for this are stuff like GDB on Linux, maybe Windbag on Windows. Pick your poison. But what these allow you to do is actually hook up to the target. In much the same way that if you could see the wheels of a safe turning as you turn them, you'd be able to understand what's going on, and you'd be able to unlock the combination if you had X-ray vision. So debuggers are X-ray vision for real-time applications. The stuff you kind of want to look for is almost similar to the static analysis. You want to look for where the key functions are being performed as they're performed, and what's in memory. So which function A calls which function B, what does it do, what variables does it send, kind of what's going on. There's a more powerful version of debugging, often referred to as concolic analysis. So this is much more complex than we can really talk about here. This is really interesting if you're interested in this stuff. But what this does is it combines powerful kind of mathematical, theoretical techniques with a live debug view of the application. So in the example of the safe wheel, think about it as providing a video X-ray of the safe wheels moving to a powerful computer that will simulate it in its memory and tell you the combination. So these are really powerful if you can use them, but they have quite a high learning threshold. But these are some good examples of ones that have been known to find a lot of vulnerabilities at scale. Which brings us on to fuzzing, which is another common technique. We're going to break fuzzing down into two halves. So black box, which is where we kind of send random messages to the server without really knowing what's going on within the server. This is really quick and dirty to do. So one tool there is Redamza that you can do. There are lots and lots of others you can find. You can even just cat dev urandom to the binary, to the server, and see what happens. Generally a bad idea, but you can do it. So the idea here is we just send lots of random data, see what the binary does. Maybe it crashes, right? Or maybe it magically unlocks the authentication, and you've found some kind of bypass. And this allows you to discover undefined behavior, unsafe behavior, for example, buffer overflows. But a more powerful type of fuzzing we can do is what we call coverage-guided fuzzing. And this is the fuzzing most people mean when they say fuzzing. And we're talking about tools such as AFL, libfuzzer, hongfuzz are three of the famous ones. But again, many others exist. These typically assume access to the source code. You can actually do them on binaries, but again, it's less efficient and it's much more tricky usually. So the way these work is you take the source code, you recompile it with the fuzzer, with coverage insertion, you take some sample input, and in the case of network protocols, this sample input is typically taken from packet captures. So run TCP dump, capture some sample packets, that's your fuzzing data. You mutate it, so you kind of play with the data, randomize little bits of it, and then you feed it to the program. And the fuzzer notices what the program does with it, and then it recombines it in this loop of constantly changing the inputs, submitting them, until it kind of figures out every path through the application. And it finds lots of crashes, typically. We'll go on to talk about it a bit more, but this is quite difficult for network protocols. This is just a kind of summary of those techniques. So I've kind of ranked them their vague complexity or difficulty levels. Source code, very easy to just look at it, whereas, for example, fuzzing and reverse engineering typically takes some dedicated time to set up and get your head around. Fuzzing specifically often involves a lot of upfront time building the harness, and then running a fuzzing campaign, and then analyzing crashes, and it's a whole loop. So it takes a while. These aren't quick techniques necessarily. But those are the techniques. So in part one, we looked at the IPMI protocol. In part two, we looked at protocol techniques, protocol security in general. And in part three, we looked at some more practical techniques. So what I'm now going to do is go through an example of something I did in the previous couple of years, which was apply these kind of protocol analysis techniques to a real-world protocol and end up being able to find some exploitation, some exploits in it. And we'll show you kind of how this was found and how this works. So again, we're going to go back to IPMI. Remember, the protocol that allows you to unlock motherboards or reboot motherboards. We're actually not going to be talking about a physical BMC implementation. We're going to be talking about a software version. So a software BMC actually controls virtual machines. So it runs in user space on top of a Linux kernel in this instance. You talk to it over a socket. And what that can do is send command signals to, for example, QEMU machines to allow you to reboot them, stuff like that. But it allows you to kind of simulate a BMC, as it were. And we're going to show several techniques that we just talked about. Not all of them, the kind of subset that were actually involved in the kind of real research. And then show how this resulted in a vulnerability and how to exploit it. So first off, source code analysis. So first off, clone the code, look at it in the editor. I just spent some time with it. I just spent a couple of days looking through it and making notes. The next thing, run some of those automated tools. So in this case, I just ran the free version of semgrep. 2 findings, which is nothing. Both were false positives. So really nothing to be concerned about. Oh, and I should say this is written in C, C99. I wanted to show off this other source code analysis tool called Wegley. It's quite similar to semgrep, and it's not as It's not unique. It's similar to tools such as Coach&L, if you've heard of them. But this is a bit of a more flexible C source code scanning tool. So you can kind of encode your own patterns and then look for specific things. So if you have an idea of a vulnerability that might exist in source code, you can encode it yourself as a signature and then quickly run it from the command line. Again, we run it. We don't find anything that interesting, but we learn a bit more about the code. So then what we did was a fuzzing campaign. This took about 2 weeks. So what it did is rewrote the source code, hooked it up to libfuzzer, captured inputs from sample packets, and then ran a fuzzing campaign. So a fuzzing campaign involves taking those inputs, fuzzing the application, examining the crashes, examining how this works, and then repeating the whole process in a loop. And while doing this, we found out that fuzzing network protocols is hard. The reason for that is that fuzzing is quite well optimized for programs with a single input and a single output. So let's say a PDF to text application. It reads a PDF file and it spits out text. A network protocol does not have a single input and a single output. A network protocol has lots and lots of little inputs, i.e. packets arriving at any point in time, maybe on multiple threads, maybe on multiple protocols, maybe on multiple ports, on multiple hosts, or whatever, and then lots of outputs, right? So it writes packets back. So to fuzz a network protocol, as we learned here, involves quite a lot of work to get the harness to simulate the various potential inputs that the network can receive and the various internal states to get high coverage. We do find some things. We find a couple of ways of crashing the application with null dereferences. There's an example of some source code here where you can kind of see the red variable comes from a packet. You send a packet with a ridiculous number in this field, and you go out of bounds in memory and it crashes. But nothing exploitable. So we didn't find a buffer overflow that led to mode code execution. We didn't find anything like that. These are minor memory issues, really. Which brings us onto the state machine analysis. So in state machine analysis, again, we want to kind of figure out the graph of the application. So the way I want to show this is we're making a decision. Is the protocol good? Is it a straight line like this? Or is it bad? Does it have these kind of red bypass steps? So if we look at the code for our dummy protocol, bad looks like this. If it receives a message, I process it. So what would good look like? Good would look like this. We insert another if statement, and we effectively say, if you receive this message, check to see that you are actually authenticated before processing it. In other words, check that the state is good. So now, when we look at the IPMI source code, what are we going to do? We're going to kind of conjecture that there's two scenarios. There's the good scenario and the bad scenario. And we're going to look at the code. Which one do we think it is? So this is, I've just kind of extracted it here. This is the core code. Now, if you're not familiar with C, that is an array of function pointers. And if you can see that if statement, all that if statement says is, if I receive a packet, call the function for that packet. So that is no checks on kind of ordering, no checks on state, and we're going to say that that is actually a vulnerable state machine. There's no checks that packets are being sent and received in the right order here. So it's bad. And that's interesting to us. So now we're going to look at some debugging, and we're going to kind of dive into the memory of that application. As I said, it was a C application, so what I did was I hooked GDB up to it. So you might not be able to make out, but I'll kind of explain the core things you want to be looking for in these outputs here. This is GDB printing the contents of memory of the application. So what I'm saying is print the state of our session. And this example is what the state looks like before any authentication has happened. So everything here is zeros. Then what we do is we authenticate. And we look at what memory looks like during a session. And now we can see that actually there's a bunch of stuff in there. So we can see our user ID has been filled out. Remember, the users from IPMI. We can see that there's some cryptographic function pointers there. And crucially, at the bottom, all that green stuff, that is cryptographic data. So when we are authenticated, there is memory that represents our cryptographic authentication material. The interesting thing is what happens afterwards. So we log out and start a new session. And what we see is that this is the same. So the cryptographic data, those keys in green at the bottom, have persisted between the sessions. Also our privilege level, which you can see just right at the bottom there. So that's quite interesting to us. So these variables are not being correctly unset between sessions. We are in session 1. We see that we have the key data and the privilege level, but then if we open another connection, we actually inherit those properties from it because the memory is the same. And that's something we learn via debugging. We can tell that from the source code, but it's easier to see live. So to summarize our different findings, the source code analysis found that the state machine was, let's say, vulnerable. There was no checks on message ordering. The fuzzing found some memory issues, but nothing we can really exploit. And the debugging found that memory is staying in the application when it should be cleared and persisting between sessions, which we're going to come to exploit later. So what we now want to do is take the IPMI protocol and show how these bugs can lead to an exploit, a practical exploit. We're going to look at an authentication bypass. So we as an attacker are going to show how you can send an IPMI command, an IPMB command, i.e. turn off the machine or retrieve the thing or change the secure boot settings without authenticating. So IPMI uses RACP to authenticate, as we talked about at the beginning, and this relies on you knowing a password. So as an attacker, we don't know the password. That's why we want the authentication bypass. Now, because we found the kind of weakness of the state machine, we know that we don't actually have to send packets in the order that is shown there. So we don't have to obey the rules that are laid out in the protocol specification. We're going to actually skip the crucial authentication steps, and we're just going to send data. So our attack is going to look like this. We're going to open a session, and then we're just going to send data, and we are never even going to try to authenticate. And that is going to, we think, allow us to send valid data to the machine and turn it off, let's say, without authenticating. So what we do is write some proof of concept code with Scapy. If you've not come across it before, it's a really great Python library that allows you to manipulate network packets. So it comes with built-in libraries for a lot of known protocols like TCP/IP, but actually you can create your own. So here what we do is we use Scapy and Python to create an IPMI implementation and then craft the exploit packets we want and then send them, receive outputs, process the outputs, etc. And this is our attack. So first off, like I say, we just open session, and then we send the data, right? So we've never authenticated. That's our attack. Unfortunately, we get an error here, and it's a bit of a cryptic error code. So we go back to the source code. Where does this error code come from? It comes from here. You don't need to read that source code, but the crucial part is, what that is saying is, OK, I'm actually processing your command. You are authenticated, but you are authenticated with privilege level equals 0. Remember, users have privileges. Because we skipped authentication, we were never assigned a real privilege level. So we stuck at 0. And this has led to us actually, ironically, not being able to exploit our own vulnerability. So now what we can do is we can confirm that by opening this up in GDB. So we saw the memory earlier. If we look at the privilege variable in our exploit session, we have a privilege of 0. So OK, we've authenticated, but we can't do anything. So we look at the source code. Where is this privilege level set? It's set in RACP1. So remember the first stage of authentication, which we skipped. So let's modify our exploit. Let's reintroduce authentication message 1 and skip the second authentication message. So we're now going to open a session, send the RACP1, send the data, and we should be good to go. So we do that, and we run into another error. In this case, let's say it was an error with the user that was being submitted. So we have privileges, in theory, but the way that the RACP processing works won't allow us to go any further with this exploit. At which point, we can actually remember, do you remember the memory issue? So memory was being left between sessions. What we can now begin to do is build an exploit that goes between 2 different sessions. So we're going to combine our 2 previous exploitation attempts and join them together with the fact that if we set a variable in memory, it persists even after the session is closed. So our new attack looks like this. And I'm going to show a little table here of the key variables. So active represents, is the session considered valid? So a 0 is no, a 1 is yes. User ID is, do you have a valid user that's allowed to talk to the server? And the privilege level is your privilege level. So we begin with the kind of second half of our exploit. We open a session, and we send a username. So active is 0 because it closes the session. User ID 0, it was an invalid user. We're not allowed to go further. However, because of a quirk of how the code worked, it actually assigned our session's privilege level before we did any authentication, really. So we actually leave a 04, which means admin, in the privilege variable. And then what we do is we start our second session. So this is actually our original attack. We open a session, and as you can see here, our session is now active because we have sent a valid open session request. The user ID still happens to be 0 because, again, we've not actually sent a valid user yet. However, the privilege level is 4 because of the mistake in the memory, because of the mistake that the code did not clear this variable between sessions. And because we have a valid session with a privilege level of 4, we send a command. And the command goes off. That's not a very exciting proof of exploitation, but that is a log from the server saying, I've turned the computer off. Well done. And at no point have we set a password. We've never exploited buffer overflow. We've never done anything like that, really, have we? All we've done is change the order of messages and choose the properties of them, and that's allowed us to bypass authentication. Oh, thank you. So what could this be used to do in real life? All we've showed is that we can authenticate without really authenticating. If we go back to some of that prior research, you can see that if you have access to IPMI, you could do some really nasty stuff, such as interfering with the host operating system. You could try and gain access to the host, or you could just turn devices off and be annoying. Now, when we discovered this, obviously we want to look at what's the actual impact here. So I scanned the internet for this. I found a special kind of signature that this protocol, that this implementation has that others don't. And fortunately, there were no instances of this online. So there's lots of Dell iDRACs, there's lots of HP ILOs, there's lots of Supermicros, but there is no version of this particular software online. And the reason, and that's a good thing. The reason is that the people that are running this, and I know that there are people running this, but the people that are doing so are sensibly doing so behind firewalls, on internal networks, on local host interfaces, for example. So fortunately, very little public impact. After finding these things, we reached out to the open source software author. They were really great. They were really helpful. They put up with my really terrible C code when I submitted patches. I'm not much of a C coder anymore. But yeah, so we kind of went through the disclosure process. Fortunately, very little real-world impact. So it was a nice proof that you could bypass authentication, but it wasn't the end of the world, unfortunately. Well, fortunately, unfortunately for kind of impact of convincing people that this is a serious thing in terms of protocol security and state machine attacks. So how can you fix these issues? So first off, if you're writing software, crucially network software, you need to remember that security issues don't just come from the contents of packets. So you don't just have to check, is this SQL safe? Is this buffer the right length? You need to check that they're being processed in the right order. Also, clear up memory when you're done with it to stop those weird issues with sessions. But if you have a state machine such as this, what you need to do is cut those weird paths off and ensure that there's one correct, clean, good path through the protocol. And you do that typically by inserting a variable in the state which says, I am now authenticated. And then when you process data, you check that state. So you say, has the user authenticated? Yes. And then you're hopefully safe. And that's it. So thanks very much for attending. I've got a slide of references for you all there. I would encourage anyone with interest in this space to take a look at some of the tools that we talked about, maybe have a play around with some open source protocol implementations, see what you find. I think there's a lot more to be found out, for example, in the IPMI protocol, and I think that there's a lot more to be found out in terms of state machine attacks. So yeah, knock yourself out, find some software to play around with, and hopefully make them more secure. Thank you very much, everyone.